Assalamualaikum and hello everyone. Welcome to our video presentation for course MAT263 Linear Algebra. We are from group CDCS 1434E and today we will be presenting the topic Gauss-Jordan elimination method, which is one of the key techniques used to solve system of linear equation. Our team members are Nur Aina Ayuni, Nur Azwani Zafitri, and Elisha Irdina. Let's begin. The Gauss-Jordan elimination method is a technique for solving linear equation problems. Carl Friedrich Gauss, who popularized Gaussian elimination in 1809 while working on his square calculations, is credited with laying the groundwork for this technique. Wilhelm Jordan likely invented the better version that converts equation directly into reduced row echelon form in 1888, even though the approach today bears his name. Jordan's contribution simplified the procedure by eliminating the necessity for back substitution. Gauss notation gained popularity over time, and by the middle of 20th century, these row echelon forms were often referred to as Gaussian elimination. The main purpose of learning the Gauss-Jordan method is to provide a clear and structured way to solve system of linear equation. This method allows us to simplify the system step by step, making the solution easier to obtain without guessing. It also helps us identify whether a system has a unique solution, many solutions, or no solution at all by observing the reduced row echelon form of the matrix. Additionally, the Gauss-Jordan method is an essential tool for finding the inverse of a matrix through a row reduction. Overall, mastering this technique builds strong foundation in matrix operation and enhances problem-solving skills needed in advanced mathematics, engineering, and computer science. There are three basic row operations used in Gauss-Jordan elimination. First, we can multiply a row by constant. Second, we can interchange two rows. And third, we can add a multiple of one row to another row. This operation allows us to reshape a matrix without changing the solution of the system. A construction company wants to build a small house. The total cost depends on three main materials: cement, sand, and bricks. Different contractors offer packages with fixed amount of these materials at different prices. The company wants to find out the exact price of each materials. To do this, they will create a system of equations using the package prices. Then, they will use Gauss-Jordan elimination to solve the equation and find the unit cost of each materials. This will help them choose the cheapest and best supplier.
A construction company received three package offers where package A consists of 10 bags of cement, 5 cubic meter of sand, and 200 bricks with a total price of Rm 2,150. For package B consists of 8 bags of cement, 7 cubic meter of sand, and 150 bricks costing Rm 1,870. And for the last package is package C consists of 12 bags of cement, 6 cubic meter of sand, and 180 bricks with a total price of Rm 2,310. The purpose of this study is, first, we aim to help the company determine the actual cost of 1 bag of cement, 1 cubic meter of sand, and 1 brick based on supplier package prices. Second, we form linear equations from the given package information and represent them using augmented matrix. Finally, we solve the system of equation using the Gauss-Jordan elimination method to determine the most cost-effective option. So we move to the real solution where step 1, we need to define our variables. So let X represent the price per bag of cement, Y will represent the price per cubic meter of sand, and Z will represent the price per brick. So based on the supplier packages, we form the following linear equations. So for package A, we have 10x plus 5y plus 200z equal 2,150. And for package B, we have 8x plus 7y plus 150z equal 1,870. And for the last package, package C, we have 12x plus 6y plus 180z equal 2,310. Step 2, we need to write the system in augmented matrix form. So for row 1, we have 10, 5, 200 and 2150. For row 2, we have 8, 7, 150 and 1870. And for row 3, we have 12, 6, 180 and 2310. So this matrix represents all three equations in a compact form, which allows us to apply Gauss-Jordan elimination. Step 3, we start the Gauss-Jordan process by making the leading entry of row 1 equal to 1. This is done by dividing the entire first row by 10. So the matrix in first row will be 1, 1 over 2, 20 and 250. Step 4, we replace row 2 by row 2 minus 8 times row 1. So the matrix in row 2 will be 0, 3, negative 10 and 150. This step is done to eliminate the value below the leading one and move closer to row echelon form. Step 5, we replace row 3 by row 3 minus 12 times row 1 to eliminate the entry below the leading one. Then the matrix in row 3 will get 0, 0, negative 60 and negative 270. Step 6, we divide row 3 by negative 60 to make the leading value of row 3 equal to 1. Then the matrix in row 3 will be 0, 0, 1 and 9 over 2. Since the matrix in row 3 have reached RREF, because we obtained the value of Z which is 9 over 2, this means the price of one brick is Rm 4 ringgit 50 cent. Step 7, we replace row 2 by row 2 plus 10 times row 3 to eliminate Z in row 2. So the matrix in row 2 will get 0, 3, 0 and 195. Step 8, we replace row 1 by row 1 plus 20 times row 3 to eliminate Z from row 1. So the matrix in row 1 will be 1, 1 over 2, 0 and 125. Step 9, we divide row 2 by 1 over 3 to make the leading entry of row 2 equal to 1. Then the matrix in row 2 will be 0, 1, 0 and 65. So the matrix in row 2 have reached RREF because we obtained the value of Y which is 65. This means the price of 1 cubic meter of sand is Rm 65 ringgit. Last step is step 10. We replace row 1 by row 1 minus 1 over 2 times row 2 to eliminate Y from row 1. So we have reached RREF in row 1 which is value of X is 185 over 2. This means the price of one bag of cement is Rm 92 ringgit 50 cent.
Using the Gauss-Jordan elimination technique, the system of three linear equations representing the contractor's package prices was successfully transformed into reduced row echelon form, which is RREF. From this final matrix, the values obtained were 92 ringgit 50 cent for each bag of cement, 65 ringgit for each cubic meter of sand, and 4 ringgit 50 cent per brick. These values satisfy all three original equations when substituted back, meaning that each contractor's package pricing aligns consistently with the calculated unit cost. This confirms that the system has a unique and valid solution. The result provides clear insight into the true cost structure of the materials offered. The results show that Gauss-Jordan elimination is an effective method for breaking down complex pricing packages into their basic components. In this case, each contractor offered different combinations of cement, sand and bricks, making it difficult to compare their prices directly. By modeling the packages as a system of linear equations, we could mathematically isolate the unique price of each material. The elimination process systematically removed variables until each could be solved individually, showing the strength of matrix-based methods for handling multiple variables simultaneously. Additionally, the consistency check confirmed that the derived values are accurate, as all substituted results match the total package prices given by the contractors. This shows that the pricing data provided was internally consistent and that the final values accurately reflect the underlying cost structure. With the true unit prices known, the construction company now has objective data to compare offers, evaluate cost effectiveness, and potentially negotiate better pricing. This approach not only saves time but also reduces financial estimation errors during project planning. In conclusion, Gauss-Jordan elimination is an effective and reliable method for solving system of linear equations. In this study, the method was successfully used to determine the unit cost of construction materials. This shows how linear algebra can be applied in daily life, such as budgeting, cost comparison, and financial planning. For example, Businesses and individuals can use similar methods to compare prices, manage expenses, and make better purchasing decisions. Overall, this application highlights the importance of linear algebra in helping us solve real-world problems efficiently and make informed decisions in everyday situations.